Hi everyone, my name is Kamil Borzym. I am a software engineer at Allegro. Thank you for the invitation to this meetup. Thank you for the nice introduction. And today I will tell you how to eavesdrop on mobile apps. So yeah, that's actually the true title of this presentation. The one that you saw on the presentation before was generated by ChatGPT to be more attractive to you, but topic remains the same. So first, let's see the overview of this presentation. And before that, a short note. I will not talk about SSL-pinning at all. I mean, majority of mobile apps, at least on App Store for iOS, do not even use any extra secure SSL-pinning at all. All you need to do for those apps is to just install the proxy tool certificate on the device, and you can just see the whole network traffic just like that. So for the simplicity, I will just show the plain HTTP traffic in my presentation, but the presentation will look just almost exactly the same as if we are trying to intercept HTTPS encrypted communication. So if you want to bypass SSL-pinning, that's probably a topic for yet another presentation. Let's start with the overview. First, I will tell you about, it's a hard word for me to read, coral reef. Then, after this introduction, I will tell you about 4 methods of intercepting network traffic. First, using a system proxy, then custom DNS, then iptables, and finally, LLDB. So why do we even try to eavesdrop on mobile devices? So probably you will need debugging capabilities during the development or while fixing some mysterious bug, or while testing either to see the communication or to mock the communication when the backend is not yet there, while testing for security vulnerabilities, then to analyze performance to see how many requests are there really in the mobile app, how large are responses for those requests, then to verify the compliance, maybe with the company standards, maybe with legal requirements. And it probably will be very helpful when you're integrating with some existing backend when you want to exchange some logs with the backend teams. So before I show you those 4 ways of eavesdropping, the topic 0, kind of theory, coral reef, and I mean it, the coral reef on the picture, actual coral reef under the water. Those coral reefs, those are built when tiny coral animals called polyps build hard skeletons made of calcium, and over many years, those skeletons accumulate on top of each other, and we get something like that. So the same way, new technologies accumulate on top of the existing ones. And I will show you the iOS networking stack as an example of such coral reef. It doesn't matter if it's an iOS or Android. iOS will be just implementation detail for the whole presentation. The idea will be basically the same for, or similar, not the same, for Android. So first, let's try to see this coral reef. Let's send a plain HTTP GET to http://bin.org/get to get a resource. And we'll do this using the C language and standard POSIX library, standard functions available in C for network communication. So first, let's see the skeleton of the program. First, we need to include a couple of headers available on all Unix-like systems, standard library for development in C. Then we are going to provide main function, and this main function will contain 5 blocks, 5 code blocks. First block will do some setup. The second block will do the hostname resolution, will translate it to the IP address. Then we are going to connect to the remote server. Then we are going to send a request. And finally, we are going to receive a response. So now I'm going to quickly show you actual code for each of those blocks. If this is too small, I think you have additional screen there, but I guess you are looking here, so the font size is okay. So the first thing we need in this setup block is to define the host name, then the port number. I mentioned to you we are just using plain HTTP, so port 80. Then we need a path that we want to access on that remote server. And we also need some file descriptor for the socket. Also some additional data structures that will be used to hostname resolution and to specify what IP are we going to connect to. We also need a buffer for the data that we are going to either send or receive, and also the buffer counter. First thing, we need to resolve the hostname. So let's fill the structure, the request structure with zeros. Let's specify a couple of additional parameters, and let's actually try to resolve the hostname using standard POSIX function get address info. It takes a hostname, a port, and it will return an IP address. In case of any error, the program will just exit. And in case we didn't manage to resolve the hostname, the program will also just exit. Okay, so we have an IP address in this result structure. Now we need to connect to that remote server. So first thing, we need to create a socket that will be used for the communication, and we'll specify a couple of additional parameters to select the type of this socket. In case of an error, we'll just exit. The socket is also created using the standard POSIX function socket available on all the Unix-like systems. Then we need to connect to that particular server using the IP address passed in the parameters. In case of any error, the program will exit. Again, there is a connect function, standard function from the POSIX library. At the end, we can just release the IP address. It won't be longer needed. Now, we need to send the request to that server. So let's fill the buffer with the HTTP request. This is get, then path, then version of the HTTP, and hostname as one of the headers in this request. So we're going to put this into the buffer, and as the next step, we're going to send those bytes to the socket using again the standard send function from POSIX library. In case of an error, the program will just exit. The final part is to receive the response from the server. So let's create a loop, and let's try receiving bytes using the receive function from POSIX library on the socket. And as long as we manage to receive anything, any bytes, just put a 0 at the end, because we are going to print it as a string. So we are just going to print the bytes as we receive them as a string. And after this loop, the program will finish. We can release all not needed stuff. Let's see the whole program. The font is small, probably not readable from that distance. Fortunately, engineers over many years created a better way to do networking. So let's do this again. This time, let's try to request for encrypted http://bin.org/get. Also in C, but this time using Core Foundation networking framework, which is available on Apple platforms. So let's try the code again. We will import a couple of additional headers. For all the people dealing with Android, forgive me talking about iOS. Please don't concentrate on like the details, but please to try to follow like the overall logic of this code structure. So we're also going to provide the main function. Then we need to parse this time the whole string URL as URL. Then we are going to create a HTTP message object with a get HTTP method. And the only thing we need to connect to the server, we just need to open a stream to reading the bytes. So this opens the stream. In case of an error, the program will just exit. We also need to create a buffer to receive bytes from the server, to receive the response and the counter. And again, similar loop, let's receive bytes until we can, as long as we can receive something from the socket, as long as server is sending us just anything, let's print it to the console. And that is it. We just need to close the stream and release a couple of additional structures. So this code, it's much cleaner than the previous one. It's shorter. Also provides encryption, just like that. But anyone of you still using that nowadays? I guess not. Again, engineers created a better way to do this. So let's do this again. This time using Objective-C. Sorry for Objective-C. It's part of the history. So let's talk about it for a while. Let's not concentrate on the language, which looks terrible, but on the overall logic. So after many years, we have a foundation framework. Let's import this framework. That's all we need. Let's create main function. Let's parse the string with URL as NSURL object. Let's get the whole networking infrastructure. And we also need a Lambda function to do the completion. Yeah, that's the correct way to do this. I can see in the first row. So the syntax is strange, but let's not think about this. All you need to know is that in this callback, we want to just print the data we are going to receive to the console. So we have everything. Now we can start the request. Let's create the data task for that URL with that completion handler. And let's just resume the data task. And we also need to wait for the background thread to complete. So we are going to start a run loop, which will wait until everything completes. Yeah, it looks much cleaner. Yeah. Okay, there is still many things that could be improved here. So let's do this again. Let's do this for the last time. This time using modern Swift. So let's import the foundation. Let's create an URL by parsing a string. Now we're just going to get the data and the response using try-await kind of coroutines to receive the data. And let's just print it to the screen. Can we do better? Maybe, but that's enough for this introduction. Okay, thank you. Approved. So this is how mobile engineers, at least for iOS, do networking nowadays. I guess on Android it was kind of similar over the years. Can you see the coral reef? I will show it to you. This is the diagram of the coral reef. On the bottom you have C with POSIX library. Then on top of that you have C with core foundation networking, which actually uses POSIX library underneath. Then we have Objective-C with foundation that actually uses core foundation networking that was almost nothing written. It's still being reused after so many years. And finally we have modern Swift. And yeah, modern Swift infrastructure still uses some Objective-C underneath. Maybe not everything, but there is still a lot is being used. Beautiful coral reef. That's the end of the introduction, and now I will actually show you the 4 methods to eavesdrop on mobile communication using the system proxy. So take a look at this very simple diagram. On the left you can see a mobile device, and in the center there is a laptop in the same local network. The laptop runs a proxy server, and we will use it in a while. On the right there is a Llama server, and sorry, it has nothing to do with Facebook, with large language something. It's just a coincidence. It's just a server that returns the information about those fluffy animals, the llama. You get it. So nothing to do with Facebook. If we have an app that sends a HTTP request to that server, that request will travel inside the IP packet. HTTP request in the packet knows about the Llama server because of this host name header. But IP packet doesn't know about Llama server at all. Instead, it knows about the target IP address. So usually this packet will be just passed by to the Llama server. But what happens if we configure the mobile device to use local proxy server instead? So this time, HTTP request looks the same, but IP packets will be just redirected to different IP address. This address of a local proxy server. The truth is I'm lying a bit because as soon as you configure the proxy, the standard of the proxy requires this get feed to actually be the full URL to the resource, but it looks like proxy tooling doesn't matter, will accept this request anyway, so it just works. And yeah, we can tell that HTTP request isn't different from the original. So this IP packet will be passed to the proxy server, and the proxy server will just rewrap the IP packet and send it to the true Llama server, to the true target IP address. Simple as that. Which tool should you use for that? There are many tools available for this job. I'm sure everyone and each of you have own favorite tool for doing the job. I will use my favorite tool, which is MITM proxy for this presentation for the all the demo sessions, but it doesn't matter which tool actually we are using. So let's start the demo. On the left, you can see a terminal. I will run a MITM proxy in this terminal in a while. And on the right, there is a screen of a real iOS device. So let's first check what we have here. It's Llamastagram. It's application to see Llama pictures. You can browse the pictures. You can like it or dislike it. Social apps for llamas. Let's try to see the network traffic. Let's run the MITM proxy. And in order to see anything, we need to reconfigure the Wi-Fi connection on that device. So let's provide a custom proxy IP address. This is the IP address of my local machine in the local network, and the port number default for MITM proxy 8080. Now, as we go back to the Llama server, you can see that we can see some photos requests. And if we try to like or dislike a photo, you can also see a request to like Llama. So yeah, now we can automate liking our own pictures or something. Let's try to see traffic of another application. There is an application called Burkanizer to reserve a desk in the office. So let's clear that view and let's see the map of the office. As you can see, we have many desks. So let's pick the desk number 8. The desk got reserved, but we can see no network traffic, so we cannot automate this activity. Proxy doesn't work for the Burkanizer. Let's try to understand why. Let's take a closer look at the Burkanizer application on the dynamic libraries being used by that application. As you can see, the application uses Flutter. And in fact, if you try eavesdropping on any Flutter application, at least on iOS, you would see no traffic in the proxy tool. Does it mean they have SSL-pinning? No, there is no SSL-pinning. So what is so special about the Flutter? Flutter uses something called Dart. It's a runtime for Flutter. On the screen, you can see a fragment of the source code for Dart socket implementation. And as you can see here, the socket create function uses POSIX socket function, this function that I showed you at the beginning in C. There is also a second Dart function, connect, that uses POSIX connect function to connect to the remote server. So it looks like Dart skips the whole networking coral reef of iOS and just uses plain POSIX functions. And fast experiment will show you that setting the system-wide proxy on iOS devices will only affect URL session networking. So taking a look at the coral reef one more time, we can put iOS proxy settings at the Objective-C level, and neither CF networking or POSIX functions are affected by setting iOS proxy settings. As for the Flutter, it operates on the lowest level. It uses the POSIX functions. Flutter does not care about iOS proxy settings. And can we do something about this? Yeah, I will show you another method of eavesdropping the network communication. This is using a custom DNS server. So let's first try to review how DNS really works. So mobile device asks for asks the internet to resolve the burkanizer.com address. This is also not the real address. I don't know if it even works, just made up example. And a router will just return a resolved IP address for this hostname. Let's try to use this laptop in the middle to run as a custom DNS server. How would that work? So after setting system DNS for this mobile device to this local laptop, all DNS queries will hit the local DNS server, and using the server we can just overwrite those circles, actually the responses, to redirect all traffic to the local laptop. And in case DNS proxy returns the IP address of this local address, we are basically going to intercept the whole traffic. For all the other requests, they will be just passed to the router and to the internet. Which tool could you use? And to be honest, I tried a lot of them and can only recommend DNS crypt proxy. It can be installed on your machine using brew, and I learned that DNS is not a single unified protocol because it can use either UDP, TCP, HTTPS, and this tool proven to work on the majority of cases, at least for me. So let's try to use that tool. Let's see all the configuration that is needed on that tool. So we need to find that section to enable something called cloaking, which is used to override the DNS request. And we just need to uncomment this line and provide this cloaking rules txt file. So let's also create this file. And as you can see, I have just one override. And actually the burkanizer uses elastic bin stock for its backend. So it's an AWS service. And providing this kind of configuration, we will redirect all the requests for the burkanizer backend to my local machine. So how did I learn the actual hostname? I didn't even have to decompile the app. I just dumped all the strings and it was used in a plain text. So here we have it, and let's start the next demo. On the left, you can again see the terminal, this time with two tabs, and we'll run the meeting proxy on one of those tabs and custom DNS server on the second tab. On the right, you can see a real iOS device. So first, let's start by running DNS crypt proxy using the configuration that we have just prepared. As you can see, it started warming up. It's started asking many DNS servers to cache some information about IP addresses. Let's also run the meeting proxy using the port number 80, because using DNS, we can only override the IP address, not the port name. Let's reconfigure the Wi-Fi connection. let's provide custom DNS. Let's remove the IP address of my router, and let's provide IP address of my machine with the proxy server. Okay, now we can run the Burkanizer. As you can see, there is a request for all the reservations. I have no reservations, but let's try to reserve a desk. We can also see the request for the map of the office with all the available desks in that office. And let's pick one of those desks. As you can see, we also have a request for the reservation. Okay, we can see the response. We can automate it. But what about Chinese marketplace app Chemu? Let's try to search something in this app. Maybe some memory device, some memory storage. Unfortunately, the app is not fully translated. Yeah, it happens, but it works. Okay, it's returned some SD card, but we can see no network traffic. And why is that? Let's check the source code of the Flutter again. So we can see a lookup address function that you cannot see my laser pointer, but it returns an IP address. So it's doing hostname resolution. So as you can see, the implementation uses POSIX function to resolve the hostname get address info. What is the issue with the Chinese app? Well, it looks like some Chinese apps don't use those POSIX resolvers at all. Why? I don't know, but I can guess. Some countries are very interested in monitoring internet traffic. I guess using custom DNS can make client-server communication a little more reliable than when using just the default government DNS. But it's just a guess. Nevertheless, this application does custom DNS resolution. Let's go back to the coral reef diagram. DNS settings will apply to the POSIX function level, but of course only when the application is using this POSIX resolver. So how to eavesdrop when custom DNS infrastructure was implemented within the app. And now we'll talk about the third way of eavesdropping by using iptables. Iptables are usually learned during some university course and later usually forgotten after the graduation, but it looks like it's pretty handy in real life, so let's check how can we use it. So let's again see the simple network diagram. So all the Chemu IP packets are usually transferred to the local router and then they go to the internet. And in case we have control over the router, we can do something about it. There is something called DNAT, Destination Network Address Translation. And we can use this mechanism on our local router to just redirect all the IP packets from the router to, for example, local machine with HTTP proxy server. And this proxy will just send all the packets again to the router. This time they will end up on the actual Chemu server. What tools do you need? Well, the only required tool here is just a modern router. And actually, Krzysiek Kocel told me there is a little nice box that you can plug in after your networking router. Maybe Krzysiek will remind the name when he's on stage. But yeah, there are a couple of methods to do that. My router allows me to enable SSH server, so I can configure iptables directly using terminal. So let's see iptables in action. On the left, you can again see terminal with 2 tabs, and I will log into my router to configure iptables on the first of those tabs, and I will run meeting proxy in the second tab. On the right, again, real iOS device. So let's try first to check the IP address of the Chemu server. We have the IP address. We'll need it in a while. Let's now connect to the router using an admin account, and let's add the iptables rule. Let's add it to the table NAT, to the rerouting chain, for the protocol TCP, for the source IP address of my iOS device. You can see on the right. So this is the IP address of that device, and destination IP would be the IP address of the Chemu server. Now we also need to choose a target, what to do with that request. So we are using dnat, and we want to override the destination IP address. Yeah, I needed to use Google to actually do this. I cannot remember myself. We providing the IP address of the machine. Before applying the rule, let's run the meeting proxy, and let's run the iptables. Okay, the rule was added. Let's try to search something in the Chemu app. As you can see, there is a request for the home screen. So they are using English for the API. It may be convenient. And we can also see a products with a query disk. So looks like iptables does all the job for us. On the networking coral reef, iptables really smashes all other methods. You could use it when you have a control over your router. But what if you don't control the router or use, for example, VPN? A VPN creates a tunnel from your device to some remote server. So being in a control of a router doesn't change anything. So do we have other options? If you try to use iptables, always remind to clean the configuration later, because the device will not work. So always try to deconfigure what you did. Yeah, it's tricky. So let's talk about the last way of eavesdropping, using an LLDB, which is a debugger used on Apple platforms. I think it is the easiest and the fastest way of eavesdropping, and looks like this method was not really described yet on the internet, and I'm doing this presentation publicly for a second time. So yeah, I'm showing this technique publicly. What tools do you need? The first tool is a jailbreak, but it's really optional, because if you want to eavesdrop third-party apps, you would need a jailbreak to do that, to connect with debugger. But if it's your app and you just want to intercept all the traffic from that app, jailbreak is not really required. And of course, you need a debugger, in this case, LLDB. For this presentation, I have an LLDB already connected to Chemu app that is running on a jailbroken device. So before going to the demo, let's see the fragment of header of POSIX socket. On the screen, you can see a structure and a function. And the structure describes all the data required to connect to a socket, and the connect function on the bottom connects to this socket. So it takes the structure as the second argument. In order to use the proxy, we would need to have to change contents of the structure a bit. So we would need to have to set the port number to 8080 used by meeting proxy, which is 1F90 in hexadecimal, and also the IP address to the IP address of our local machine, which is C0A8028 in hexadecimal. And those structures are not really visible in the runtime, in the debugger, so you will need to calculate all the offsets by hand. So I replace type declaration on the left with byte sizes. And the first and the second byte, first and the second value takes 1 byte each. So the third value of the port number is at the offset of 2 bytes. So knowing all of that, This simple pseudocode will allow you to override the port number and IP address on that structure. So second argument, which is a pointer, plus 2 bytes, and we're just going to put there 6 bytes, which is a port number and the IP address. So I'm basically going to create a breakpoint on the connect function and add a custom debugger command. And this command is memory write argument 2 plus 2 bytes, and remaining are just the bytes that we're going to override. For other debuggers, the syntax can be different, but it will work basically the same. So on the left, you can see a terminal. I will use it to run with proxy. On the right, you can see a real jailbroken iOS device. And there is also an Xcode in the background running that LLDB. I will show it to you in a while. So let's first run mit proxy. Okay, now there is an Xcode. I'm going to add a breakpoint. I will zoom in a while, just adding the breakpoint. Let's zoom in. And we need to create a breakpoint on a symbol, which is connect function. Not any connect function, but the connect function located within the main dynamic library. And we have a breakpoint. We just need to add debugger command when calling that command connect function. So memory write argument 2 plus 2 bytes and 6 bytes that going to be stored on that memory location each time the breakpoint is being triggered. And we can click to automatically continue after evaluating. So this setup is ready. Let's try to search something on Chemu app. Yeah, and it works. So I already disabled the iptables configuration. So using this method with debugger, we've been able to see the network communication. I encourage you to try this method at home and at your own app. It can be very convenient when developing just any app on your local machine. I have few ideas how to automate this, but I think just using the breakpoint is enough and it's usable. So it's time to sum up. So I showed you 4 ways of intercepting the network traffic. First is kind of a default kind of starting point. System proxy is very popular, but it's somehow limited, at least on iOS, to URL session infrastructure or to WebView. Then custom DNS. It is nice because it allows you to control over like the exact matching of the host name, and don't you can you can target just the host names that you are interested in, but the tooling is pretty inconvenient. I had to start 2 servers. It's not really convenient. We also have iptables, very powerful, but requires admin access on the router. And there's also an LLDB. It works with VPN. The downside is you either have to have jailbroken device or you only are able to debug the single app and no WebView, because WebView, at least on iOS devices, is a separate process. If you know any other cool methods of intercepting HTTP traffic, I would be happy to talk about them during the break. And this ends my presentation. So thank you for your attention and have a great evening.
Thanks a lot. I enjoyed the presentation. Oh, there's a mic. Nice. That's so cool. All right. I enjoyed the presentation very much. Really insightful. And I just wanted to maybe kind of clarify something or just add something to the presentation.
Sure.
As a Flutter developer, I sometimes struggle with the issue that you showed, that the Dart uses its own networking, I would say, stack. But recently, in like last 2-3 years, it's possible to actually switch to just a native iOS stack.
As a developer.
As a developer, and you can just, your app can be just using the iOS stack, which has some benefits, like re-implementing all that Coral Reef is not easy, and there are some bugs or some quirks that are different between native iOS apps and Flutter apps. So just to make your life easier as a developer, you can just choose to use just the iOS stack, and then you can just use Proxima or anything like that.
So it also makes things easy for security researchers, and let's keep
Keepers as well.
fingers crossed for that.
And QA, definitely. So I can just add to my 2 cents, and that's something that I just found out like last year. So,
Thank you.
Hey, thank you for the talk. There is one tool I think you should have mentioned, which is called Frida. What do you think about it?
When I mentioned automating this method of intercepting network traffic, I was thinking about writing something like a plugin or something to the Frida. I'm not really sure right now what method of intercepting network traffic does the Frida uses. I need to check that.
So basically it would be the same as LLDB, only works for jailbroken devices, but it runs directly on the device itself, so you don't need Xcode for it.
Yeah, so with LLDB, with breakpoints, it really slows the application if you have many like requests. And with Frida, I think it's way faster. And you would probably do exactly the code that you showed us with overwriting the same function in Frida.
I will check that definitely. I think I was looking for that in the internet. I was also checking the Frida and it was working differently, but let's verify it.
As addition to the one method, I saw your presentation before when we made rehearsal, but there's one thing that came to my mind, that you could use a kind of like old school method, having just a network hub that mirrors all the traffic on the other ports. So this is something that can be used as well instead of iptables method, if we are talking about unencrypted traffic.
Yeah, so you could buy this device on OLX for 80 zlotys, or you could use it iptables if you have on your router.
So thank you for the talk. I noticed that WebView does not work with LLDB, right? Because I presume it's a different process, right?
Yeah.
But so is there a method actually to intercept the traffic coming from the iOS system? That's basically to see what all these system services like, I know, ShareSheets, App Store, all of them are sending and receiving from App Store. Is there a way that you can see all the traffic that iOS device actually sends and then receives?
I haven't tried that. Maybe Frida allows something like that. I think the WebView is like running on kind of daemons. They are called really agents in Apple infrastructure, and they are just like any other process. So you can attach to that process if you have a jailbroken device.
Okay, so I think that was all. Yeah, let's thanks Kamil once again for his great talk. I feel a great need to buy something on Czemu, but now I'll invite you all to the pizza outside of the spot, and we'll see each other in like 15-20 minutes.